Okay. Well, uh, I've been mentioning this each time, but I want to tell you that these four, I think of them as checks. Uh, okay, so four checks. To always do on internal loads. Actually, it's five. What? Yeah. Okay, so the first two are the ones we've talked about. dm dx has to be equal to v. That has to be true point by point. And then the second one is negative dv dx has to be equal to q. And then there are three checks on endpoints. The first one is the shear force is equal to 0 at an endpoint. If and only if. So the only way you can have the shear force equal to 0 is if you meet these conditions, and the only way these conditions can happen is if the shear force is equal to 0. There's no vertical point force at that endpoint.
Is that like a if and only if symbol?
Yeah. Okay, so distributed loads are not point forces. So you can have distributed loads at the endpoints, but there just can't be any force vectors happening there. The fourth one, 3, 4, and 5 are all sort of similar. The second one is tension is equal to 0 at an endpoint. If and only if. What do you think this condition is going to be?
Horizontal.
Yes, exactly. No horizontal point force at an endpoint. And then what do you think the fifth one is going to be? Any guesses?
Rotational.
What?
Rotational.
Yes, exactly. So the bending moment is equal to 0 at an endpoint if and only if there's no point couple at that endpoint. The most common way that we have point couples is if that endpoint is a fixed joint, like a weld joint with a wall, like a cantilever beam or something. So we've had a problem or two where there's an applied couple at the endpoint, but most of the time it's done from a fixed joint. So if you don't have fixed joints and you don't have weird stuff with point couples, then there's not going to be any bending moment at the endpoint. I want to redo a problem where I use these requirements to solve the problem. I think everybody's probably thought about that before. That's come up once or twice in class. Like, well, if you know you have these derivative relationships, can you just start at the simplest case and then integrate up to get the internal loads? You can do that. It usually is as much of a pain as doing it through Newton's laws like we're doing it. And then if you do that, you don't have any way to check your work. So I prefer to do it by using Newton's laws and then going back and using these as checks. I think that's a better way to go. But let me show you what you would have to do if you were going to use these derivative relationships. So this is using the derivative relationships. To calculate the internal loads. And let me just put here that I think it's better to use Newton's laws and then use the derivative relationships as checks. Okay, well, so here's the problem we're going to do. We've done this one before. We have a cantilever beam. With a triangular distributed load. And let's say this has a maximum of 1,000 newtons per meter. The length is 3 meters. The mass is 50 kilograms. And we want to calculate the internal loads. This is an easy one to do with these derivative relationships because there's only one cut. And at x equals 0, we have 0 tension, 0 shear force, and 0 bending moment. Okay, so our constants of integration are going to be simple. Okay, so this is an especially nice one. For integration. Okay, well, start with a free body diagram of the whole thing. We have the triangular distributed load that's given. We have the stuff happening over here. So I'll call that reaction R and then a reaction couple MR. And then we have the weight force. This has a weight of 490.5 divided by 3 to get the distributed load. And so we have a uniform distributed load of 163.5 newtons per meter. Okay, well, we're going to start by, using the fact that, so what we know is that negative dv dx is equal to q. And these are functions of x. And so we can use that to say that v as a function of x is the integral of negative q of x dx. And so we need to come up with that function q of x. That is, we need to come up with the total value of the distributed load at any x value. That's easy for the uniform distributed load. It's just 163.5, but it's, you know, we have to come up with a function for that triangular one because whatever x you use, you have a different value of that distributed load. Okay, so we're going to do that with that equation for the line. So let's say q for the uniform as a function of x is just 163.5. So that one's easy. But q for the triangular is mx plus b. The slope over the whole length of this line, we have a rise of 1,000 over a run of 3 times x. And when x is equal to 0, that triangular distributed load is 0. And so this is just equal to 333.3 repeating x. And so the total then is just the sum of these two functions. So that's 333.3 repeating x plus 163.5. And so now we're going to use the integral relationship. The shear force as a function of x is the integral of, well, negative of the integral of this q that we just got, 333.3 repeating x plus 163.5 dx. And so that is negative 166.6 repeating x squared plus 163.5x plus a constant of integration.
Minus?
Yeah, thank you. Okay, so what are we going to do with that constant of integration? This constant of integration, you use boundary conditions to find. So if we know what the shear force is at one of the endpoints, we can use that to calculate this. Okay, so boundary conditions. We know that the shear force at x equals 0 is equal to 0. Why do we know that?
Because of rule number
Yeah.
3.
3, exactly. So there's no vertical point forces at that endpoint, so we know that this shear force is 0 there. And this is equal to negative 166.6 repeating times 0 squared. We're just plugging 0 in for x. Minus 163.5 times 0 plus c. And so this says c is equal to 0. Okay, and so now I'm going to update this function. We know that the shear force is negative 166.6 repeating x squared minus 163.5 x. And now we're going to go to the second one. We're going to use the fact that, so we know dm dx as a function of x is equal to v. And so we can rewrite this as m as a function of x is the integral of v dx. So m of x is equal to the integral of negative 166.6 repeating x squared minus 163.5 x dx. And so this bending moment as a function of x is this is negative 55.5 repeating x cubed minus 81.75 x squared plus another c, I'll call that c2. I don't know why I was putting these parentheses in. So there's our function for m, okay? And now we have to use the boundary conditions again. Again, because there's no point couple at the left end, we know that at x equals 0, m is equal to 0. So go to our boundary condition. So m at x equals 0 is equal to 0, and that's equal to negative 55.5 repeating times 0 cubed minus 81.75 times 0 squared plus c2. And so c2 is equal to 0, and we get that m as a function of x, this is my updated function after the boundary conditions, m is equal to negative 55.5 repeating x cubed minus 81.75 x squared. C2 is 0. So there you go. Yes?
Let's go back to the free body diagram.
Yeah.
I'm kind of just confused why the gravity force isn't like 163.5x.
Yes. The 163.5x comes when you re-express this Q, this distributed load, as an equipolant point force. Okay, so what we do there is, so if we have this cut where this has a height of 333.3 repeating x, and then this distributed load is 163.5, and then we have these things. Okay. Then the next step is now we calculate the area and the centroid. Okay, you got it now, or?
I get it now.
Okay, anyone want me to follow through on this? Okay, so right, when you doing that integral approach, since we have the relationships between the actual distributed load and the shear force, we never have to represent anything as a point force. So we never had to take that step, that's why.
So really, it should always be the area of those distributed loads plus whatever constant you need to like shift it to like the point you are on the number.
Yeah, I guess that's right. Yeah, that's right. And one other thing I wanted to say about these constants of integration. So this was easy and fast. And I did one that was easy and fast because I didn't want to waste a lot of time on it. But if you have more than one cut, this gets messier because this was easy because, for one thing, our boundary condition was at x equals 0. And for another thing, all of our values were equal to 0. But if we had a second cut, we would have to match all these things up. The right side of one cut would have to match up at like the seam between those two functions. And so you do one of these things, calculate the constant of integration, then figure out what the value is at the end where the next distributed load starts. Okay, then you do the integrations for the second cut, and then your boundary condition says I have to match these internal loads to what I had at the right end of my other one. Anyways, I don't recommend doing this, using this for solutions anyways. I mean, I tend to think like for engineering stuff, the challenge isn't how fast you can get stuff done. The challenge is how you can know that you did stuff right, you know? And so giving up, saving 10 minutes or whatever, but doing it by giving up a way to catch some mistakes or whatever, to me never makes sense. And so that's why I'd say just always do it with Newton's laws and then use this stuff as checks. Yes?
If you have more than one cut, does the check still work?
The checks do not work, but you can still calculate those internal loads at that point and use that with this same boundary condition approach, So like if you know that at x equals 2, you know that the bending moment is equal to negative 284 or whatever, then you can say negative 284 is equal to negative 55.5 repeating times 2 to the third minus 83.75 times 2 squared, blah, blah, blah. And you can still calculate that C value the same way. In D-form, we'll have to do that kind of stuff, not for this, but it's basically because of these same relationships. But here we don't have to do it. Any other questions about that?
Is this kind of the more traditionally taught way then?
No. Well, I mean, I think at the U they do spend a couple weeks doing this, maybe instead of half a class or whatever, but it's not really. I mean, I think they tend to do it the same way I do it, I think. Yeah.
Minus the awesome table.
Yeah, that's right, the table.
I just talked to a guy yesterday, he's in my statistics class.
Yeah.
He's like, I literally did substitution for my entire statics class.
Oh, yeah, yeah.
Yeah.
Too bad for him.
Uh-huh.
Still work with it. That's what we're talking
Yeah. Okay, so notice that in all of the examples we've done so far, the internal tensions have just been constants. We haven't ever had internal tensions as functions of x. Why is that? Yeah, we're about to get that.
Because they've always been perpendicular. Like our loads that are functions of x are
Uh-huh.
perpendicular to the.
So, okay, so Yes, that is why. Because we have never had horizontal distributed loads, you know, and all of those functions come from, well, the fact that the shear force is often a function of X comes from distributed loads. Okay, so what happens though? So what if you want to find the internal loads for members in a structure? I mean, that seems like a pretty obvious thing to want. Like you calculate the external loads in a structure so that you can figure out what kind of materials you need for this thing not to break, and calculating internal loads is a big part of that. So like what if you have something like this? Let's say there's a 500 Newton force here. And let's say the two masses are the same, let's say 30 kilograms each. Let's say, so this is an equilateral triangle, and the lengths are 1 meter. Then a free body diagram of one of these members after you calculate those external loads is going to have a distributed load like this. And you have up here, you'd have your F12 and your 500 Newton force. And down here, you have your RA. So how would we calculate the internal loads in something like that? Where, I mean, to think about internal loads, we just always think about this thing being horizontal. But now, you know, you have a distributed load that isn't perpendicular to the beam. Okay. So here are the steps that we're going to take. So first, we're going to re-express any point forces in a coordinate system with the x-axis pointing along the beam. And we're going to do this with rotation matrices. So the way these rotation matrices work is if you have a coordinate system like this, and you know your vectors in this coordinate system, so you know your vector components in this coordinate system, and you want to re-express them in a coordinate system like this, where this angle theta is the counterclockwise angle from your original to your new coordinate system. And you want your vector components in this coordinate system. Then your rotation matrix, capital Q, is cosine of theta, sine of theta, negative sine of theta, cosine of theta. And then you're just going to multiply that matrix to your force vectors. So, okay, in the example above, so here is our member, and we have a coordinate system like this. And the coordinate system we want has the x-axis pointing along the long axis. Okay, so what's the counterclockwise angle from our starting coordinate system to our new coordinate system? 60, yep. Positive 60 because it's counterclockwise. And so our rotation matrix is cosine of 60, sine of 60, negative sine of 60, cosine of 60. And so that is 0.5, 0.866, negative 0.866, 0.5. And so that 500 Newton force in the example above what are the vector components of this 500 in the original coordinate system?
500.
Yeah, 500, 0. So now we have our rotation matrix. Multiplied by 500, 0. And that is, what is that?
I got minus 476. Does that sound bad? That seems wrong. Minus 476. Oh, I'm in radians.
Oh, okay. Let's see. So that's just 250, negative 433.
So now you can think of that as like, yeah, your original coordinate axis rotating in that direction.
Right. So the thing to be careful of is don't think of the vector rotating. Think of the vector staying still and the coordinate system rotating around the vector. And for actually doing that calculation, all of your calculators will do that. If you just enter these values into a matrix and just use the regular multiplication symbol with a column vector, it'll give you that answer. Okay, so you'll do that for all of the point forces. And then the second step is you're going to express your distributed load as a vector in your original coordinate system. Okay, so up until now, these downward distributed loads, we've just been calling that like a scalar value. But now we're going to think of this in components. In our original coordinate system, this only has negative y components. Okay, so what was the value of this? So 30 kilograms. So this has a magnitude of 294.3 newtons per meter. So our Q vector as a function of x, in this case, is 0, negative 294.3. Okay, then re-express this in the new coordinate system using the rotation matrix. We're only going to do this for uniform distributed loads because we're only going to do it for weight. So you're not going to have to worry about using this with functions of x or anything. But so now we have, our 0.5, 0.866, negative 0.866, 0.5, times our vector 0, negative 294.3,